Hello, welcome to Maths with EJD. In this video, I'll be talking about random variables and distributions. And of course, this video will be focused on discrete random variables. But first of all, let's talk about random variables. So what is a random variable? That is the question to start with. So a random variable is a function that assigns a numerical value to each possible outcome. We've talked about outcome, event, and things like that in a previous video. So a random variable is a function that assigns a numerical value to each possible outcome, of a random experiment, such as the result of rolling a die, drawing a card, or measuring the temperature. So when you carry out a random experiment, so the system by which you assign a numerical value to your result is what you can call a random variable. Now, a random variable can be either discrete. So in this case, it is taken on a countable set. It is taken on a countable set of values. Like the number of heads in a coin, like the number of heads in coin tosses. You know, a coin has one head and one tail. So if you toss the coin 100 times, you can actually, so the value you get, if you count the number of heads, is actually discrete because you can actually count them separately like that. So a random variable can either be discrete, taking on a countable set of values, like the number of heads in coin tosses, or it can be continuous. It can also be continuous. So if it is continuous, that means it is taking on any value, within a given range, like the exact time it takes for a chemical reaction to occur. So this one, it's difficult to actually pin it down to say a chemical reaction is occurring in 1 second or 5 minutes or anything like that. So it can be 5.2, 5.33, 5 point whatever, depending on whatever you're measuring with. So that is the idea of continuous. Okay, so that is about random variable. How about if we talk about distribution? What is a distribution on the other hand? You know, we are talking about random variables and distributions. First of all, so distribution. So a distribution of a random variable, a distribution of a random variable is a mathematical expression, or is a mathematical description, a mathematical description that provides provides the probabilities of all possible values the variables can take. So for instance, if you toss two coins, right? If you toss two coins, remember the sample space. Let me give this as an example. If you toss two coins, the sample space will be it can be head, it can be head, tail, it can be tail, head, or tail, tail. Okay, that's the sample space, right? So if you say X represents a random variable, that is number of heads. So X is a random variable, which is the number of heads, right? So it means that whatever the number of heads is what X takes. So in that case, you can have the probability, right? So for instance, if this is X and the number of head, so if you have 0 heads, it's possible to have 0 heads. You can have 1 head, 2 heads. That's the maximum you can have for when you toss 2 coins. That's the maximum you can have. So in this case now, the distribution, that can be like a function, right? Because we said that is actually a mathematical description, so it can actually be a function. So the probability that you're going to get 0 head when you toss 2 coins is actually 1 out of 4, right? Because there is 0 head here. So the probability you're going to get 1 head is here, 1, 2. So that's 2/4. And then the probability you're going to get 2 heads is actually 1/4. So usually when you add up those probabilities, you're supposed to get 1, which of course this gives you, because 1/4 plus 2/4 plus 1/4 gives you 1. All right. So if we take X to be number of heads that occurs when 2 coins are tossed. So this is like these are the variables now. These are the variables, and then these are the probabilities. These are the probabilities of those outcomes. Okay. So so we have that for now. Let's move on to focus on discrete random variables. So that's what this video is going to be focused on, now that you know what random variable and distribution are. Okay, so let's talk about discrete random variables. Discrete random variables. Okay, so when you hear the word discrete, it's just know that it's about countability, that you can count something. So a discrete random variable is a type of random variable. The type of random variable that takes on a countable number of distinct values. A countable number of distinct values. Okay, so these variables are often used to represent quantities that result from counting, such as the number of successes in a series of trials. The number of arrivals at a service point, or the number of defective items effective items in a batch. So as far as you can count, then you're talking about random, discrete random variables. So now this leads us to the idea of probability mass function. Probability mass function. Probability mass function, PMF. Probability mass function, PMF. So the probability mass function that is PMF of a discrete random variable, X gives the probability that X takes a specific value. So that's the kind of thing I did the other time. Well, tossing two coins, right? So we have the sample space. So, if the the random variable X can actually take value 0 if the focus is on two heads, the number of heads, right? So random variable X can take 0, meaning when there is no head at all. That's when you have tail. And the probability that happens is actually 1/4. So that's actually what the probability mass function in this case. On the other hand, too, probability that when you roll two coins, you get one head is actually 2/4. That's where you have head, tail, or tail, head, and that's 2/4. 2/4 is the probability mass function now. So the probability mass function of a discrete random variable X gives the probability that X takes a specific value. Okay, so mathematically, if X is a discrete random variable, and X, the other time, right, I said the random variable is X. So this is our random variable now. Random variable is X. But when I got here, I used small x because this small x now is actually a particular case. It's a possible value. So X talks about the possible value. Okay. So random variable is X, but the possible values the random variable can take can be represented as small x. So mathematically, if big X is a discrete random variable and X is a possible value that X can take, then the probability mass function is denoted as this. The probability that the random variable takes a particular value X is actually equal to a function f of X, which is called the probability mass function. So here now, so where f of X satisfies the conditions, just two conditions. The first one is that f of X is always greater than or equal to 0. So we talk about the non-negativity as one of the axioms, non-negativity of probability function. So f of X is greater than or equal to 0. That is for all possible values of X. Whatever X is, f of X is always greater than or equal to 0. That is true of the previous example because each of these 1/4, 2/4, 1/4, they are all greater than or equal to 0. Okay, they are all positive, all greater than or equal to 0. Then the second condition balances it out. The second condition is that the sum of all probabilities, is actually 1. What that means is that when you sum up all the probability mass function, you get 1. And again, that is true for what I also did here. So 1 over 4 plus 2 over 4 is 3 over 4. And then 3 over 4 plus 1 over 4, all of that leads us to 4 over 4, which is 1. Okay, that's 4 over 4, and that is 1. So those are the two conditions a probability mass function needs to satisfy. That each probability for all possible is greater than or equal to 0 for all possible values of x, and then the sum of all probabilities is 1. So, and that is why we already know that probabilities are always bound between 0 and 1. So it can be less than 1, and I mean it can be less than 0, and it can be greater than 1. So if you're working probability and you get a probability to be negative or more than 1, check again. Something is definitely wrong. So let's look at some examples of discrete random variables. So examples of discrete random variables. And the first one would be binomial distribution. Binomial distribution. So that's a very good example of a discrete random variable. Okay, so the binomial distribution, don't forget we are looking at random variables and distributions, right? So, and then we have looked at discrete random variables. So under that, what kind of distribution? A distribution is associated with a random variable. So if you're talking about discrete random variable, what kind of distributions can we have? So, and the first one is the binomial distribution, which represents the number of successes in n independent Bernoulli trials. Of course, what is a Bernoulli trial? It's actually a Bernoulli trial is an experiment. Bernoulli trials are experiments with two possible outcomes. So any trial with two possible outcomes is a Bernoulli trial. So experiments with two possible outcomes of either success or failure, head or tail, so tossing a coin, for instance, tossing a coin can be a very good example of Bernoulli trial because you either get a head or a tail. So a Bernoulli trial is an experiment with two possible outcomes, success or failure. So in that case now, the probability mass function for a binomial distribution, or a binomial random variable x, representing the number of successes. So if success for you is getting ahead, for instance, in a coin toss, okay? So when you count the number of heads, when you get head, that's your success, right? When you get tail, that's failure. So what the distribution is actually talking about the number of successes or whatever your expectation is, So representing the number of successes is given by this probability that the random variable big X takes on a particular value K, or if you like, you can call it small x, and that is equal to n combination K, P raised to power K, 1 minus P raised to power n minus K. Okay, so at some point I'm going to talk about permutation and combination so you can understand what this is. But I mean, for the purpose of this particular video, I'm going to explain that along the line. Okay, it's probability that the random variable x takes a particular value K is actually n combination K. That is select K out of n, multiply by the probability of getting of succeeding, whatever success is to you, maybe getting ahead. So the probability of getting that raised power k minus multiplied by the probability of not getting what exactly you want, raised power n minus k. So let's break down the components. For instance, where n is the number of trials. N is the number of trials. More like tossing a coin 100 times. So in that case, n is the number of n is equal to 100 because it does the coin 100 times. Then next you have k. K now is the number. K is the number of successes. K is the number of successes, and that is actually such that 0 is less than or equal to k, is less than or equal to n. So it means that if in a coin toss you're expecting that a head shows up, so it's possible, I mean, whatever, it's possible that you toss the coin 100 times and the head doesn't show up at all. So it means that the value can be 0. Or if it's possible you toss the coin and then the head shows up all the time, 100 times. Or, of course, the most likely situation is that you're going to get a value which is between 0 and n. Okay? So that's the value of k. It's the number of successes. And when I say successes, right, it is whatever expectation you have. For instance, maybe the success for you is when 3 students enter a class, what is probability that you have a girl, among the students that enter a class? So for you, your expectation is about the number of girls. So that is your success in that situation. So it's depending on whatever you define success as in your experiment. So P now is the probability. P is the probability of success in each trial. Probability of success in each trial. Okay. So probability of success in each trial. That's a P. And of course, you have N combination K. N combination K is simply N factorial divided by K factorial divided multiplied by N minus K factorial. So this is actually the binomial coefficient. This is the binomial coefficient. So it will always give you a value, a numerical value. So it is called the binomial coefficient. So can we take an example under this? So, example. So imagine that, okay, suppose you are flipping, a fair coin. A fair coin means the head and tail are in order. A fair coin 5 times. That's the same thing as flipping 5 coins at the same time. So if you're flipping a fair coin 5 times, right? And you want to find the probability of getting exactly 3 heads. Exactly 3 heads. So, normally, right, if you follow what I taught you in the second video where I talked about probability with coins and dice, right? So normally you should start doing something like, so you do head, tail, head, tail, head, tail till you get, of course, you're going to get 2 raised power 5 outcomes. That's 32. So you're going to have head, tail, head, tail, head, tail, head, tail, pair for 16 times, making 32. And then you go head, tail, tail, and so on. But then that's actually a lot because you're expecting 32 outcomes. So with this now, you don't have to go that way. So in this case now, you've been told already here that n is equal to 5. So you have 5 trials. Okay. The probability of either getting head or tail is 0.5. But here, our focus is on the number of heads we need to get. So, of course, it's 0.5 since the coin is fair. So it's possible that you can manipulate a coin such that because maybe you win when a head shows up, then you manipulate it such that there's a higher chance of head always showing up. But for a fair coin, it's 50-50. So probability that a head is what shows up is 0.5 since the coin is fair. And of course, K is 3. That is the Of course, just like you know already, K is the number of successes. So the number of heads you're expecting to get. And you want to find the probability of getting exactly 3 heads. So K is equal to 3. So in that case now, the probability mass function, the PMF would be probability that X is equal to 3. So K is 3, right? And that is equal to N combination K. That's 5 combination 3. Then P, which is probability of getting a head, raised to power K, that's 3, multiplied by probability of not getting a head, that's 1 minus 0 0.5, all raised to power N minus 3, that's 5 minus 3. So if you do this, of course, 5 combination 3 by the side, 5, 3 is like 5 combination 3, which is 5 factorial, 5 factorial all over 3 factorial into 5 minus 3 factorial. That's like 5 factorial over 3 factorial times 2 factorial. Of course, you know, this is 5 times 4 times 3 factorial. I stop at 3 factorial because I know there's 3 factorial down here that will cancel that. So, and 2 factorial is 2 times 1. So, 5 times 4 is 20. 20 over 2 is 10. So, you see the whole of, so that 5 combination 3 is actually 10. So, this is 10 multiplied by 0 0.5 raised to power 3. Okay, well, let me, okay, we have 0 0.5 raised to power 3, then multiply by another 0 0.5 raised to power 2. Okay, so that is 10 times 0 0.125 times 0 0.25. So if you multiply all that out, the result is equal to 0 0.3125. Okay, 0 0.3125. So in that case, we can say that, so the probability of getting exactly 3 heads is 0 0.3125, like that. So if you do the long method I explained earlier about the head tail head thing, you get the same result. But that's a longer way to get here. So, but with PMF, we are good to go. So we just apply the formula and that's fine. Okay. So another example of discrete random variable, since that's what we're talking about, right? You remember? So we're talking about examples of discrete random variables. That's random variables that take uncountable, countable outcomes, so to speak. So we go to the next one, which is the Poisson distribution. The Poisson distribution. Poisson distribution. So don't forget the binomial distribution is actually is related to Bernoulli trials, where you can expect only one of two, which are with two possible outcomes. So for the Poisson distribution, on the other hand, let's say, so that the Poisson distribution is used to model, the number of times an event occurs in a fixed interval of time or space, given that these events occur independently and at a constant average rate Okay. So in the case of Poisson distribution, right, the probability mass function for a Poisson random variable is, X is given as this. Probability that X takes the value of K is actually the same thing as lambda raised to power K, e raised to power minus lambda over K factorial. So in a sense, we actually, Poisson is used for rare events, some kind of rare events. We're going to see a practical example later. So where first of all, the lambda is the average rate. Lambda is the average rate or mean number of occurrences, mean number of occurrences in the interval. Okay, and then next, K itself, just like we saw before, is the actual number of occurrences. K is the actual number of occurrences. 0, 1, 2, and so on and so forth. Okay, so let's take an example. So suppose a bookstore receives an average of 3 customer complaints. 3 customer complaints per day. And that's the idea of something happening within a specific interval. So here now the interval is like a day. Suppose the bookstore receives an average of 3 customer complaints per day. The number of complaints per day can be modeled using a Poisson distribution with lambda equals 3. No, lambda is the average number of occurrences, right? And here we are told the average of 3 customers per day. So with lambda equals 3, right? Okay. So in that case, the probability of receiving exactly 5 complaints in a day is this. That's probability that X is equal to 5. Now K is 5, right? So K now is 5. So P of probability that X is equal to 5 is now, lambda raised to power X, lambda raised to power K from the formula, lambda raised to power K. So our lambda is 3 and K is 5 now. And e raised to power minus lambda. So again, lambda is 3, the average rate of occurrence. All of this divided by 5 factorial, that's K factorial. So 3 raised to power 5 is 243. Then e raised to power minus 3. And 5 factorial, of course, is 5 times 4 times 3 times 2 times 1. And that is 120. So if you put all of this together, you get 0. Okay. So you get 0.1008 when you put all that together. So in that case, we say that the probability of receiving exactly 5 complaints in a day is approximately 0.1008. Okay, so you can, since the average is 3, right, you can check. So you can actually do you can check for 3 itself, which is the average. You can check for 4 and all that and see which is likelier to happen in a specific day. So with this, we come to the end of discrete random variables. So first of all, we got to see what random variables are. So of course, a random variable is whatever you say it is in a particular experiment. And of course, every random variable can take a specific value, which is the small x, where the random variable itself is big X. And then the probability that the big random variable x takes a value small x is actually what we call the distribution. And of course, that leads us to the idea of discrete random variables, which involves countable outcomes. And then it has two conditions that each function is actually greater than or equal to 0, and then the sum of all functions is actually 1. And then looking at the specific types of discrete random variables, we have binomial distribution, which is good for Bernoulli trials, experiments with 2 possible outcomes, success or failure. And then we also have Poisson distribution for events that happen within a specified time. All right, if within a fixed interval of time or space. And that's it. If you have not subscribed to this channel, be sure to do that. And of course, hit the notification bell so you can always get alerted when a new video is released. And don't forget to comment, like, and share. See you next time. Bye.